Hi, Ji, am I audible?
Yes, sir.
Okay. So up to last class, we have finished the condition for the phase difference and part difference for bright fringe and dark fringe. So Hishma, what was the condition of part difference for the bright fringe? Yes. Condition of part difference for the bright fringe, Hishma. What should be the value of part difference for bright fringe? We have derived these things in the previous class. No. Shefullah, what was the conditions of part difference for the bright fringe? See, in the previous class, we have discussed the conditions for the bright and the dark fringes. So the bright fringes means light and light will add up, and the dark fringe means that light and light will cancel each other. So bright fringe means addition of light waves, and dark fringes means light and light will cancel each other. In a very, very simple language. So for the bright fringe, we have derived this thing. Now. For bright fringe, we have derived that phase difference should be 2 and pi. Part difference should be n lambda. And this is the R max. R max is a plus b, and I max is k times a plus b square. And the intensity, the relation for intensity was this I1 plus root I1 plus root I2 the whole square. And then we have derived expressions for the dark fringes also. For dark fringe, the phase difference is 2n minus 1 pi. Part difference is 2n minus 1 lambda by 2. Your minimum amplitude will be a minus b. Intensity will be k times a minus b square. And then we calculated the ratio of maxima and minima, which comes out to a plus b square by a minus b square. So this is what we have done till now. So let me explain one more. So we were doing Young's double slit experiment. So these are the two sources of light. This is one source. This is second source. Source 1, source 2. The light waves coming from the source 1 and 2 superimpose each other. When they superimpose each other, then they form some patterns on the screen. There were two types of pattern. One is bright fringe. Bright fringe means waves and waves will get added up. And then you have dark fringes where wave and wave will cancel out each other. So we have derived the conditions for the bright fringe in terms of phase difference and part difference. Similarly, we have derived the condition for the dark fringe in terms of phase difference and part difference. Now what we have to do is we have to calculate again the position of bright fringe and dark fringe in terms of separation from central maximum. Means if I consider this fringe, okay, let me rub it up. Let's rub it and draw it again. The calculation is straightforward, but the number have a number of So we need condition of bright fringe and dark fringes in terms of part difference. So this is your source. We call this as the source slit. This is a double slit pattern. This is slit S1 and this is slit S2. So this is double slit. And this is your screen now. This is the screen. The separation between the two slits is usually represented by D. The separation between the two slits. Separation between the double slit and the screen is usually represented by capital D. So the light waves will start from this point S. So the single source S gets divided into two sources. One is S1 and another is S2. The light waves coming from S1 and S2 will superimpose each other. When they superimpose each other, they give interference pattern. Let's consider a point P on the screen. So on P, the light waves are coming from S1 as well as the from S2. So at point P, the light waves are coming from S1 as well as S2. This is point. So light waves are coming from S1 and S2 on point P. So when they reach point P, they interfere, means they superimpose. And due to superposition, you can get a bright fringe or a dark fringe. So we'll get a bright fringe or a dark fringe will depend upon the phase difference and the part difference. So Anshika, not Anshika was not. Yashika, for what value of phase difference, the fringe at point P will be a bright fringe? Yashika, for what value of the phase difference, the fringe at point P will be a bright fringe?
Is 0.
0. Or can you generalize it?
It 2n pi.
2n pi. Similarly, if the phase difference between waves reaching point P from S1 and S2 is 2n minus 1 pi, then you will get a dark fringe. Waves and wave will get cancelled out. And if I take the perpendicular bisector, say this separation is D, so I'm taking a perpendicular bisector from here. Perpendicular bisector. Which means this separation, this one is D by 2. Similarly, this separation is also D by 2. So if I talk about this particular point on the perpendicular bisector, means this point is at equal distance from S1 and S2. So the waves reaching this point will cover equal path. At this point, ray will come from S1 as well as rays will come from S2. They will cover equal path. So this is O. So this point at the center is known as the central maximum. We call this point as the central maximum. The separation between the central maxima and point P is represented by Yn. This is Yn. So what is Yn? Yn is the separation of nth fringe from central bright fringe. So this is the central bright fringe. From the central bright fringe to the point P, the separation is Y. So Yn is separation of the nth fringe from the central bright fringe. Now we have to decide what the part difference between waves reaching point P from S1 and S2. So see, the waves reaching point P from S1 will cover a relative smaller path than the waves coming from S2 to point P. So the waves coming from S2 will cover greater path as compared to waves coming from S1. We'll calculate the part difference. So what is part difference? Part difference is simply S2P minus S1. So this S2P minus S1P is known as the part difference. Now, in the next part of the calculation, what we will do, we will try to express this part difference in terms of small d, capital D, and Yn. That is the motive of this derivation, to calculate part difference in terms of Yn, small d, and capital D. Now, so for this, what we can do is,
अरे पंखा बंद मत कर, पंखा चला के जा। क्यों?
अरे भाई मेरा आज बंद करो। So x is S2p minus S1p now. Now let's drop a perpendicular from S1 to this line. This perpendicular, the name of the perpendicular is M. So in triangle S1p, S1MP. See, in this triangle, this SM is equal to capital D. If you want to calculate MP, MP is C. From O to P, this separation is YN. From O to M, this separation is D by 2. If you want this MP, then this is YN minus D by 2. This is the separation. So your SM is D, your MP is YN minus D by 2. And this S1P is the path basically. So you need S1P in terms of this term and this term. So we can use Pythagoras theorem. So you can write that S1P is root over SM square plus MP square. I'm just using Pythagoras theorem. So SM is this, and this is it. Not just SM, but S1M. Now, if I substitute these values here, then you can say that S1P is root over S1M. How much is S1M? S1M is D. See, S1 to M, it's D. It's D square. Plus MP. How much is MP? MP is YN minus D by 2. So it's YN minus D by 2. So this is the first task, to somehow convert this path S1 to P in terms of YN, capital D, and this small d. Next, what we can do is we can write this S1P as it's D square plus YN minus D by 2 whole square, and this whole to the power half. Next, what you can do is you can take this D square outside. So when you can take D square as common. So when you take D square as common means you are dividing both the sides by D square. This is the meaning of taking common. So you take D square as common. And see, there is this power half. So we'll have half power over D square also. So here it's 1. So this will be mathematically, it will be wrong if I write it. So now you understand. Taking D square as common means dividing both the sides with D square. So that's 1 plus. This is YN minus D by 2 whole square divided by D square and this whole to the power half. So you have S1P is equal to, if you take D square to the power half, that's D. It's 1 plus YN minus D by 2 divided by capital D square to the power half. Now, the separation between the slits S1 and S2, which we represent by small d, is very, very small as compared to capital D. So we use this approximation that small d is very, very less than capital D. So under this approximation, this term YN minus D by 2 divided by D square. See, if this is small, this is also small, it's very, very less than 1. If it is less than 1, then you can use binomial theorem here. You can use binomial expansion here. This binomial expansion. 1 plus x to the power n is equal to 1 plus nx. But one can use this binomial expansion only if n is this half. If this x is less than 1, you can use this expansion only if x is very, very less than 1. So if you compare this expression with this binomial expansion, say you have 1 here, you have 1 here. Instead of x, you have yn minus d by 2 whole square. And instead of n, you have half. So if you use binomial expansion, using binomial expansion, in, let's say this is, let's call this as equation number 1. Oh, it's 1, this is 2. So if you use binomial expansion in equation number 2, then you will get S1P is equal to D. This is 1 plus. Instead of n, you are using this half. You can multiply this half here. So this is half. It's y minus d by 2 whole square divided by d square. Let's call this as equation 3. So this is S1P. So we have converted your S1P, that's the part difference, small in terms of small d, capital D, and Yn. Yn is the separation of fringe from the center max. Similarly, you have to convert the path traveled by the next wave also in terms of this small d and capital. See this path, I'm talking about this path now. S2P. So for S2P, what we can do now is we can drop a perpendicular over the screen. Let's the name, give this perpendicular the name M. So you have S2NP, this right angle triangle. In triangle S2NP. So what we can do is S2NP, S1P is the hypotenuse, which is S2n square plus Pn square. So you can write this as S2n is, it's S2n square plus, I'm just using the Pythagoras theorem. See, this is a right angle triangle. S2NP is a right angle triangle. So here the Pythagoras theorem, this hypotenuse is S2P, which is S2n square plus Pn square. S2n square plus Pn square plus Pn square to the power half. To P's. Okay, if the previous steps were clear, just tell me what is S2n, what is S2P. Okay, S2P is S2n square plus Pn square. So how much is S2n here? Hishma, what is the value of S2n?
Capital D.
Capital D. And what is NPn? What is the value of this Pn here? This P2n. This one. P2n. How much is this?
Yn.
Not Yn. Yn is up to O only. I'm asking about Pn.
Yn plus D by 2.
Yn plus d by 2. So this Pn is Yn plus d by 2. So when you use the Pythagoras theorem, you can write that S2P is S2n, which is d square, plus Pn, which is Yn plus d by 2 whole square to the power half. So there's this small difference. Instead of Yn minus d by 2, you are getting Yn plus d by 2. So if I repeat all calculations, repeating all steps like S1P, you will get that S2P is, see, this was the expression for for this thing S1P. For S2P, instead of minus d by 2, we'll get a plus d by 2. So S2P is d. This is 1 plus 1 by 2 Yn plus d by 2 whole square divided by d square. This is equation number 1. So we have S1P as well as S2P. So our motive is to calculate the part difference. See, when we calculate the part difference, majority of the terms will get cancelled out. When we start calculating the part difference, majority of terms will cancel out. So for part difference, see what is part difference? Part difference, we represent part difference with x. This x is S2P minus S. How much is S2P? It's D. 1 plus 1 by 2 yn plus d by 2 whole square divided by d square minus d 1 plus 1 by 2 yn minus d by 2 whole square divided by d square. So I just substitute the value of S2P and S1P that we have calculated in the previous section. So what we do is for part difference, we substituted 3 and 4 in 1. Now see, you can take this d as common. So you have 1 plus 1 by 2 yn plus d by, it's a very important derivation for upcoming exams. D by 2 whole square divided by d square minus 1 minus half yn minus d by 2 square divided by d square. Next, what you can do is you can just cancel this one with this one. And you can do one more thing, like you can take this half d square as common. This is 1 by 2 d square. You can take it outside. So you are left with only yn plus d by 2 whole square minus of yn minus its d by 2 whole square. See this 2d square and this 2d square, take it outside. So this d square will cancel the square. It's a lengthy calculation, but at the end you will get a very, very small relation. So your x will be 1 by 2d. So that's whole square minus yn minus d by 2 whole square. So you can just open the whole square here. Yn square plus d square by 4. A square plus b square plus 2ab. So it's twice of y into d by 2 into d by 2 minus its yn square plus d square by 4 minus twice of yn into d by 2. Now see, this 2 will cancel this 2. Similarly, this 2 will cancel this 2. And you can write that your part difference is it's 1 by 2d. See this negative sign. So the terms in the bracket the sign will get changed. So this is yn square plus d square by 4 plus yn into small d minus yn square minus d square by 4 plus yn into small d. Now you can check. See this yn square will cancel this yn square. This d square by 4 will cancel this d square by 4. And you are left with only x is 1 over 2d. See, this is yn plus yn plus yn is 2yn. Again, this 2 will cancel out each other. And you will get that your part difference is yn into small d divided by capital D. This is equation number 5. This is the relation that we needed. So this is the relation between x, which is part difference. Part difference means this difference, S2p minus S1p. The difference in the path traveled by the waves from S1 and S2. Yn is this separation of this nth fringe from central maxima is y. And small d and capital T are double slit and the screen separation.
So we will only get the question on this expression, right? Not the entire
No,
calculation.
you will be relating this with the bright and dark fringes. But yes, you can get on this expression also. So this is the first, but while deriving this expression, one should remember that we have used this approximation, that small d is very, very less than the capital. It's an easy derivation, but yes, a lengthy one. Easy calculation. You're just using a Pythagoras theorem, nothing else. In the last step, you are using binomial. Note it down.
सर ये आज का पहला टॉपिक है.
पहला topic. Samia Rahman. Samia, is this your first class with me or you have joined with a different name?
Sir, this is me, Nabil, sir.
Nabil,
My laptop isn't working. I use my
Okay.
sister's.
Nabil Ahmed, na?
Yes, sir.
Okay. Akshay, Anshika, Minashi. Where were you in the last classes?
Sir, I had exam, so I don't know.
Akshay, you were absent for maybe for the last 2 weeks, huh? So you have missed almost the entire this thing. You have missed the entire wave optics. This is the second chapter. Only one chapter is left, which is diffraction, and interference is the major part of wave optics. And Minashi, where were you?
So I couldn't join last class.
You were absent in the last whole week.
No, 2 days.
2 days, no? Monday and Wednesday.
Yes.
You missed the entire interference.
I will watch the recordings.
Omar, it's not the right method. The thing that the step S2P minus S1P is 2ID2 by S2P plus S1P. You should write the whole calculation, like from where this is coming. So the method from which this expression is coming is actual calculations lengthier than this one. So if it's your choice. If you want to memorize that thing, then it's totally different issue. But see, if you want to memorize everything, that you have, like, you should have very, very good memory, because you have around 50-60 derivations. Gautam, it's your first class with me, no?
Yes, sir. First class.
Okay. Gautam will discuss at the end of the class how we'll finish the syllabus. Huh?
Okay, sir.
So right now we're doing wave optics. We just have started the second book. So you have missed just 3 lectures of the second book, wave optics.
Okay.
3, no, not 3, 2, yes, 3 lectures. This is the 4th lecture of wave optics. We are doing interference, right? Haji, is it clear? Saifullah, Arpit,
Yes, sir.
Yes, sir.
and all those like Akshay, Nabil, Anshika, and this Minashi who were absent in the last classes, just go through the recordings of at least of interference. Just go through the recordings of interference at least. Interference is a very, very important topic of wave optics. Heinz principle is just formula-based thing. Is the thing important in Heinz principle, but this interference is very, very important. We'll finish optics by the end of this wave optics and this reflection, I believe. Wave optics and reflection. See, in second book, na, it's only the optics part which is a major one. Otherwise, all chapters are of 1 or 2 class. So by the end of this one, we'll try to finish wave optics and reflection. Can I scroll it now?
So after that, we will have a test, right?
Yes. Can I scroll it?
Sir, can you show the diagram once again? Done, sir. Sir, you can scroll down.
Sir, can you scroll up, please?
Excuse me, sir.
Yes.
Sir, for the square root is for both S1M or only M?
Square root is on both S1M plus MP. Sorry, what are you asking?
No, I mean that is it for only M or S1M?
It's for S1M. See, S1M is one side, na? This is one side. This S1, 2M. This is one side, and PM is another side. Square root is over whole S1M square plus MP square. I'm using this Pythagoras theorem that H is root over perpendicular square plus B square. Okay.
Oh, listen.
Tell me if you have written, scroll it down.
Sir, can you say how binomial expansion works? Sir, can you say how binomial expansion works?
See, binomial expansion is. You want to know the complete derivation? See, we use binomial expansion if you want to, let's say, expand something like 1 plus x to the power, let's say 7. And you say that this value of x is very, very less than 1. Then binomial expansion, the first will be 1, then 7 term will be 7x. Then you have higher powers of x also, but those higher powers, since x is very, very less than 1, so that higher powers can be ignored. So we take first two terms only. So here 1 plus x to the power n is 1 plus nx. You have higher terms also, like this is like if I ask you to square 1 plus x to the power square. So this will be 1 plus 2x. You will have higher terms also, higher powers also. But these higher powers are very small. X is small, na? So x square will be very, very small. You can ignore it. That's why we are left with the first two terms only. Yeah.
Yes, sir.
Can I scroll it now?
Yes, sir.
Saifullah, Uneeb, Noha, steps are clear?
Yes, sir.
1 minute, sir.
उमर, तुम्हें नंबर ऑफ स्टेप्स बहुत ज्यादा लग रहा है ना?
सर बहुत ज्यादा है।
बट व्हेन यू डू दीज कैलकुलेशंस इन एग्जाम्स, कैलकुलेशंस अगर स्टेप बाय स्टेप आ रही है उनको करना आसान होता है। जैसे आप कर रहे हो ना, बीच बीच में जो स्टेप्स आपको याद करने पड़ेंगे वो याद नहीं रहते। बहुत कुछ है यार रटने के लिए। अगर डेरिवेशन में भी बीच बीच में से स्टेप्स रटने पड़े ना तो बहुत प्रॉब्लम होती है। वो लगता है कि ओके 2 स्टेप्स रट लिए तो कैलकुलेशन आसान हो गई, बट वो 2 स्टेप एग्जाम में याद नहीं आता, बिकॉज यू डोंट हैव 10-15 डेरिवेशंस, यू हैव 40-50 डेरिवेशंस इन योर एंटायर। तो उन डेरिवेशंस का सीक्वेंस याद रखना ही एक बड़ी बात होती है। अब आप कहोगे उस सीक्वेंस के साथ साथ आप ये भी याद रखो कि कब किस किस स्टेप में क्या क्या चीजें याद कर लेनी है, तो बहुत अच्छी बात है। There is one easier method also to do this that we will learn in diffraction. Basically वो angular fringe separation use करते हैं। But if you look at these steps carefully, then just algebra है। Maths tough नहीं है, just algebra बहुत ज्यादा।
Sir, can you scroll up a little?
Yes, yes, yes.
Can you scroll up?
सर आपने हाफ डी स्क्वायर कॉमन लिया है ना?
हाफ डी स्क्वायर। Yes. Can I scroll it now? Yes, everyone have written up to equation number 5. Nabil, Shafullah, Ishma.
1 minute, sir.
Yes.
Done, sir.
Yes, sir, done.
Okay. Fine. So what is x, y, and small d and capital D? These four terms are clear. X is part difference. Yn is the separation from the center maxima to that nth fringe. Small d is the separation between the double slit, and capital D is just the separation between the double slit and the screen. Now, the next task in the calculation is to get the value of yn for the bright fringe and dark fringe. You need the value of yn for the bright fringes, and you need the value of yn for dark fringe. So what we can do is, so from this equation number 5, from 5, we can write that yn is, you can multiply it here, x into capital D divided by small d. Let's call this equation number 6. X is the part difference. Now I need condition for bright fringe. Condition for bright fringe. So which condition means the value of y for which the fringe at the point P is bright. Condition for bright fringe. So for bright fringe, your x should be equal to n lambda. For bright fringe, the value of x is n lambda. X is equal to n lambda. So if we substitute these values here, x equal to n lambda, let's call this as equation number 7. If I substitute 7 and 6, 7 in 6, you will get that yn is n lambda. Like instead of this x, I'm writing n lambda, capital D divided by small d. So this is the value of yn. Yn means the separation of nth fringe from the central bright fringe. If the separation satisfies this condition, then the fringe will be a bright fringe. So your n will start from 0. Your n is 0, then 1, then 2, and all. If your n equal to 0, that means it's central bright. If n is equal to 1, that means it's the first bright. Next, what we can do is we can then, after the conditions for the bright fringe, what we can do is we can write condition for dark fringe. Condition for dark fringe. Condition for dark fringe. So for dark fringe, the condition is your part difference should be 2n minus 1 lambda by 2. This is we derived in the last lecture. Huh? For bright fringe, your part difference is n lambda, and for dark fringe, it's 2n minus 1 lambda by 2. Let's call this as equation number 8. Let's call this as equation number 9. We can substitute this 9 in 6. We can substitute this 9 in 6. When we substitute 9 in 6, 9 in 6, we get yn is equal to, say it was x capital D by small d. So instead of x, you can write 2n minus 1 lambda by 2. It's 2n minus 1 lambda by 2. It's capital D divided by small d. This is the equation. 2n minus 1 lambda 2 by d. So let's call this as equation number 10. And your n will start from 1. N is 1, 2, 3, and all. N is 1 means first dark. N 2 means second dark, and all. You just keep on changing the value of n, the dark will change. Keep on changing. Now the next task is to calculate the width of the fringe. See, fringe width, all these fringes are alternate. Like if this is the screen, this is the screen. And I call this as the central bright fringe, a very, very thin fringe. It's just like a line. And the shape will depend upon the slit. If your slit are point-size slits, then it would be a hyperbolic shape. So we consider it as a line. This is bright fringe. Then for dark fringe, I can't draw black line. So let's draw some gray line. No, it's not visible. So white means dark fringe. I can't draw black over black. So this is the dark fringe. White is the dark fringe. So you have bright fringe, then alternate dark fringe. Then again, you have a bright fringe. Then again a bright fringe. Then alternate dark fringe, alternate bright and dark fringe. So what you can do is, if I ask you to calculate the width of the fringe, then what you will do? Then what you will do? You will just calculate the separation between the consecutive fringes. So although the fringes are very, very small, just to explain, I am drawing it. This is your central bright. This is your first dark. See, fringes are very, very small fringes. They're like line. This is second dark. This is first bright. This is first. We measure all separations from here, from central bright fringe. So this is the separation of first bright fringe. And then again, we have a second dark here and second dark here. Then after second dark, you have second bright. This is second bright here and second bright. So that's B2 and this is B2. Now see this. This is Y1 and this is Y2. Up to here, it's Y2. Y1 is the separation of the first bright from the central maxima, this one. And Y2 is the separation of second bright from central maxima. If you subtract Y2 from Y1, you will get this thing, this thickness. And this thickness is the width of the dark fringe. I'm again repeating, I'm drawing very, very wide fringes, but these fringes are just like lines. So if you want the width of the dark fringe, what you will do, you will take two consecutive bright fringes and you will subtract its separation. Like to get the value of second width of the second dark fringe, you will subtract the separation of second bright fringe from the first bright fringe. If you want width of the third dark fringe, that will do, you will take third bright fringe and second bright fringe, you will subtract their separations. And you will get the width of the third dark fringe. So fringe width, it is the separation between two consecutive dark fringes. This is the width of the bright fringe. Now, if I repeat these calculations, let's repeat this calculation. So what we will do, we will take nth fringe and then we'll take n minus 1th fringe and subtract them. That's it. So what is nth fringe? Nth fringe is n lambda capital D by small d. N minus 1th fringe, n minus 1 lambda capital D by small d. I'm taking something very general. You can take you can subtract second bright fringe from third bright fringe. Separation of second bright fringe from third bright fringe to get the width of the dark fringe. You can subtract fourth bright fringe separation from third bright fringe separation. You can get the width of the dark fringe. Or I can subtract n minus 1th dark bright fringe. Separation consecutive dark fringe. For dark fringe, what was the relation for the dark fringe? It was 2n. See, this is the relation. 2n minus 1 lambda d by 2. 2n minus 1, it's lambda into capital D divided by 2. This is for the nth fringe. For n minus 1th fringe, what you can do is, instead of n, you can substitute n minus 1. Minus 1, it's lambda into capital T divided by 2d. Now, what you can do is, you can take this lambda capital D by 2d as common. So you have 2n minus 1 here, minus. Here you have 2n minus 2 minus 1. So this is lambda d by 2d. It's 2n minus 1 minus 2n. See, minus 2 minus 1 is plus 3 here. So this 2n and 2n will get cancelled out. So you have lambda d by 2d, and 3 minus 1 is 2. So this 2 and 2 will get cancelled out. So you have lambda capital D by d. So this is the fringe width. This is the width of the right fringe. See, there is no n here. That means all right fringe have same width. It does not matter second, third, fourth, which right fringe are you calculating. And the expression is absolutely independent of n. So you can say that all right fringes have equal width. So the width of the all bright fringes. Similarly, we can repeat this calculation for the dark fringe. So to get the width of dark fringe, what you will do, you can take two bright fringes, consecutive bright fringes, and subtract their separation. Separation between two consecutive bright fringes, like nth bright fringe and n minus 1th bright fringe. So nth bright fringe is this, n lambda capital D by D. N minus 1 is this, n minus 1 lambda D by D. So when you subtract them, see, you can take lambda d by d as common. You have n minus n plus 1. It gets cancelled out, and you have lambda d by d. Lambda d by d now. So this simply means that in interference, all bright fringes and all dark fringes have exactly same. Even bright and dark fringes have same width. This is a characteristic of interference. When we do diffraction, we'll see that bright and dark fringes will not have same width. This happens only in interference, Young's double slit experiment. Is it clear up to this dark fringes, everyone? If you have doubts, we can discuss it. Anshika, Alia, Yashika, Noha. Doubts? Rishma?
Sir, this is single slit or double slit, sir?
Double slit. Interference, double slit. Noha, is it clear?
Slit, there's no interference.
Yes.
Sorry?
In single slit, there'll be no interference, sir.
No, single slit is not interference. Single slit is diffraction. Okay, just note it down.
So can scroll it left.
Where? Up.
Yes, enough, sir.
What, sir, what will happen if the size of the slits are not equal?
If the size of the slits are not equal, then nothing will change. If the size of the slits is not equal, that means intensity of two waves will be different. You will have bright and dark fringe.
Sir, तो
But
उनकी
if
width same
size,
होगी?
नहीं width अलग होगी. No, width same होगी. Yes, bright and dark fringes will have same. See, if slits have same width, that means intensity of light coming from both the slits will be same. The intensity of dark fringe will be exactly 0. The intensity of bright fringe will be 4 times. That will be a very special case.
Sir,
The
जो syllabus में नहीं है ना?
है. We'll do it. 10.
Okay, sir.
Haji, can I scroll it now?
Yes, sir.
Okay. Note down the fringe.
Sir, can you scroll up?
Mhm.
Thanks.
Yes, everyone have written up to dark fringe? Without dark fringe?
Yes.
No, 1 minute, sir. Sir, can you show the diagram, please?
This diagram. Fringes are alternate, huh? Central bright, then first dark, then first bright, and second dark, second bright, and all. Yes, can I scroll it now?
Yes, sir.
Okay, the next thing is angular fringe. See, what is angular fringe? Angular fringe width is just the angle subtended by the fringe on the double slit pattern. See, this is the double slit. And this is your fringe. This is your fringe. The width of the fringe is beta. So you can consider this beta as the length of arc. You can consider this d as the radius of arc. And this angle as the angular fringe width. Now you can use the definition of angle. What is angle? Angle is length of arc divided by the radius of arc. So instead of the length of arc, you have beta. Sorry, instead of angle, you have angular fringe width, which is theta. Length of arc, you have beta, linear fringe width. And then you have the radius of arc, you have d. Now, beta, we know that beta is lambda d by capital D. So it's lambda capital D by small d t. So this d will d cancel out each other and you have lambda by t. So this is the formula for the angular fringe width. It's lambda by small d. There's one more important calculation, and this is fringe width in liquid. If you immerse your Young's double slit setup in a liquid, then fringe width will change. The fringe width will change due to change in the wavelength of light. The wavelength of light depends upon the medium. The wavelength of light is different in different medium. So let's say you kept the entire setup in air, then this is fringe width fringe width is lambda capital D by small d. Then what you did, you take the entire setup and immerse in it some liquid, in some medium. Then see, the wavelength in air is lambda. The wavelength in medium will be lambda medium. The wavelength of light will change. In medium, the wavelength is lambda air divided by n. So instead of this lambda medium, you can write lambda air by n capital D by small d. Lambda air capital D by small d is beta air by n. So you can say that beta medium is beta air by n. So when you immerse the entire setup in some liquid, then the fringe width becomes 1 by n times. So just conceptual question. Just note it down, these two things. Now we'll start numericals. And I will extend class today. Huh? So don't just leave. So the whole 1.5 hour goes into the derivation only. Now we'll do some calculation. Very good. The angular fringe width does not depend upon capital D, the separation between the double slit and the screen. Angular fringe width does not depend upon.
So you can scroll it from. Done, sir.
We'll do 2 numericals and then we'll leave the class. 2 numericals on the concept that we did today. Yes, everyone have written up to here? Uneeb, Noah.
1 minute.
Yes, can I scroll now?
Yes, sir.
Okay. So that is the first question. See, the light of wavelength 5000 angstroms on a slit having capital D equal to 2 meter, small d equal to 2 mm. Calculate the separation of second bright fringe from critical maxima, first dark fringe, fringe width, and angular fringe width. Note down the question first. Okay, before writing the question, just tell me what formula you'll be using here. So, Arpit, which formula you will use in the first part? See, these are formula-based things. Arpit, first part, which formula you will use? Okay, Arpit cannot decide. Akshay, you need separation of second bright fringe from central maxima. Which formula you will use? Nabil?
Sir, width of fringes.
Not
We
fringe
find the
width.
width
Don't
of the
need
dark
fringe width.
fringe.
No, you don't need fringe width. Yashika, which relation you will use to get the separation of second bright fringe from central maxima? Okay. Yashika is not in class. Huh? Noah? She is also not in class. Oneep, which formula you will use to calculate the separation of second bright fringe from central maxima?
Sir, n lambda capital D by small d.
Yes. So this is the relation. Why n is n lambda capital D divided by small. Next, you need the separation of first dark fringe from the central maxima. Cephala, which relation you will use?
The lambda d capital D by small d.
Not lambda, 2n minus 1. Huh? 2 minus 1 lambda capital D by 2d. This relation will be. For fringe width, Meher, which relation you will use to calculate fringe width?
Sir, lambda d by small d.
Lambda capital D divided by small d. Minashi, angular fringe width, which relation you will use?
Lambda by D.
Minashi.
Sir, lambda by D.
So see, yes, lambda by D. So see, these are the formula basics. Just calculate the value, write your answer in chat room. All these are formula based. Note down the question, calculate these values and write your answer in chat room.
Sir, angstrom to millimeter कैसे होगा 10 की पावर -10
-10. Lambda is this Akshay 5000 angstrom wavelength. So just convert this lambda into meters. So multiply it by 10 raised to the power of -10. So to convert angstrom into meter, we multiply it with 10 raised to the power minus. Okay, Krishna. Okay, Noah. Okay, Oneep. Krishna, just check your calculations. Yashika, it's
So
wrong. Just check your calculations first. See, this is mm. Huh? So try just convert this in meter before starting your calculations. Huh? -3m. For second bright fringe, n is 2, but for first dark fringe, your n is 1. Okay, Nabil. No, Alia. You can check your calculations from here. The first is n lambda d by t. When you put n equal to 2 lambda d by d, it comes out to be 10 raised to the power minus 3 meter. For second part, it's 2n minus 1 lambda d by 2d. So for dark fringe, n is equal to 1. So this is for first dark fringe. Fringe width is lambda d by t. Theta is lambda by d. This is formula based. Huh? So when you do these calculations, this 2 will cancel this 2. So you have 2.5 into 10 raised to the power minus 10 and 3 minus 7 and 3 minus 4. Yes, Noah is correct. Nabil is also correct. Beta is lambda d by d. So this is lambda is 5 into 10 raised to the power minus 7 into 2 by 2 into 10 raised to power minus 3. So this is simply, it's 5 into 10 raised to the power minus 4. These all are formula based, simple calculation. So I will stop here today. From the next class onwards, we will first do some 3-4 numericals on the same concept, and we'll try to finish diffraction the next class. Diffraction is a very small topic. Even not there are not many derivations of diffraction used. So diffraction will be the last topic of wave optics. Then we will start the ray optics. See, the major portion in your syllabus which is left is wave optics and ray optics. Modern physics will, each chapter of modern physics will take just one lecture, a very, very small topic. Okay, so let's stop here. We'll continue
Yes,
this in
sir,
the next.
please wait.
Sorry?
Sir, can you show dark fringe once more?
The theory portion?
Yes, sir.
Yeah. Which is the dark portion?
Not this, the width of bright fringe and dark fringe.
Okay, if you don't have doubts, you can leave. We'll continue the next one.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.
Yes, that's it. Thank you, sir.
Yeah, Krishna. Krishna, are you still in class?
Yes, sir.
Okay. See, to finish syllabus on time, what we can do is you can do second book with me. Like the entire second book, the optics, modern physics, and everything with me. And first book you will do with Amna ma'am. Amna will start first book in 1 week. So you will have, instead of 2, you will have 4 classes in a week. For 2 days, you'll be doing second book, and for 2 days, you'll be having a first book. So that by mid-January, you will finish off all your syllabus.
Okay, sir.
Because in my batch, I already finished the first book, so I won't be starting that book again. But
Okay,
Amna
I have to
ma'am,
contact the support for that.
sorry.
I have to contact the support for that.
Yes, you can contact the operations team.